Welcome to the introduction and overview of APTI 419B, Preparation of Fine Particle Emission Inventories. This is the ninth of several modules that introduce the APTI Classroom Course 419B. This module introduces the combustion module of the classroom course. We'll cover combustion processes in general, electric generating units, boilers and furnaces, residential wood combustion, residential open burning, land clearing debris burning, agricultural burning, and wildland fire emissions. Note that the mobile source emissions from diesel and internal combustion engines, ships, rail, and aircraft were discussed in other modules. First, let's talk in general about combustion. Combustion needs fuel, oxygen, and heat. The absence or insufficiency of any of these three results in incomplete combustion, or in some cases no fire at all. Complete combustion will result in only CO2, carbon dioxide, and water being emitted. Unfortunately, incomplete combustion almost always occurs in practice because of fuel moisture or lack of air. CO2 and water emissions are accompanied by these pollutants, incomplete combustion: PM, black carbon, organic carbon matter, volatile organic compounds, NOx, carbon monoxide, methane, sulfur dioxide, and hazardous air pollutants, or HAPs. Let's look at these pollutants more closely. First, PM is emitted from combustion processes almost always as PM 2.5, but some larger particles do get emitted. These consist mainly of fly ash. Several pollutants are important climate forces, including CO2, black carbon, and methane. HAPs are also climate forces and include some of the 189 toxic chemicals listed by EPA. To estimate emissions, we must first estimate the parameters affecting combustion efficiency, such as the fuel type and the condition of the fuel. We must also know the amount of fuel consumed and any pollutant removal processes that occur. Open fires are the most difficult combustion category to estimate. Residential wood combustion is also difficult. Internal combustion engines and diesels are not as difficult as open burning or residential wood combustion, but combustion emissions from boilers are relatively easy. Pollutant emissions from incomplete combustion can be reduced in several ways. We can improve combustion efficiency, reduce fuel burned, or remove pollutants after combustion. Not all of these options are available for all types of combustion, however. This table shows non-point combustion categories in the NEI. It shows that wildland fires emitted about 60% of the PM 2.5 non-point combustion in 2005. That's about 20% of all PM 2.5 emissions in the NEI. Residential wood combustion is the second largest category. Agricultural burning is less, but it can be very important because most of the burning usually occurs in relatively short seasons. Let's look at these categories and the difficulties they present in more detail. First, residential wood combustion. The combustion efficiency of residential wood combustion is very difficult to estimate since people operate their appliances differently. Therefore, the inventory usually depends on generalized assumptions. Fuel consumption is difficult data to get because burning habits differ among households, and many households cut and split their own wood. Very little pollutant removal occurs in residential wood combustion. For open burning and open fires, we'll look at these three categories: yard waste, which includes leaves and brush; construction debris burning, which includes limbs, brush, and stumps from the clearing of land; and residential or household solid waste burning. There is much uncertainty in open burning and open fire emission estimates. Combustion efficiency is not known for any given fire of these types, so we rely on generalized emission factors. Fuel consumption is also very difficult to estimate. For example, how much leaf burning occurs relative to curbside pickup or composting in any given county? How many people burn trash in their backyards? Pollutant removal is easy since very little removal occurs. Let's discuss agricultural burning. The National Emission Inventory is evaluating ways to estimate each fire individually, beginning with version 2 of the 2008 NEI. This requires estimates of the acres of crop burned, the fuel loading in tons of biomass or vegetation per acre burned, and an emission factor, which is related to the way the fire is ignited and whether it burns into or against the wind. The general form of the emissions equation is emissions equals acres times fuel load times emission factor. Agricultural emissions data on fire size, location, and timing are being improved by satellite fire detection and by the use of ground-based data systems like FETS, the Fire Emissions Tracking System, which is used in some western states. Wildfire and prescribed wildland fire emissions are estimated using several recently developed tools: SmartFire, the Blue Sky Framework, and the Events Data Module. SmartFire and the Blue Sky Framework provide critical data needed for each fire, and the Events Module provides a place to store it in detail. These critical data needs are fire location, fire size, and the dates of the fires, the fuel type and the amount of fuel, and the fuel condition. The Blue Sky and SmartFire tools are used to calculate fuel consumption and emissions, but plume rise is calculated apart from the emissions process. The NEI uses fire location, size, and date information from two types of sources: ground-based and satellite detected. These two sources may provide different or conflicting data. These differences are reconciled by SmartFire. Fuel type, fuel condition, and consumption, along with emissions, are estimated by components of the Blue Sky Framework. Blue Sky is a framework that allows the user to select which combination of fuel models and consumption models to use to estimate emissions for any number of fires. These emissions and fire specifications are then submitted to the Events Module of the Emission Inventory System, and after checking by EPA, become a part of the NEI. There are limitations to the satellite data that's used in SmartFire. Satellites do miss some fires because of cloud cover, fires of short duration, and understory burns. Also, estimating fire size is challenging. The sensors in most satellites are not optimal for fire detection, as they were originally designed for other tasks. Also, there is uncertainty as to how many acres are represented by a detected pixel, since small hot fires may look the same to the satellite as larger cooler ones. That's why SmartFire uses both ground data and satellite reports when possible. The classroom version of APTI 419B covers additional materials and contains more detail. For example, agricultural burning in 419B will discuss the basis of NEI estimates and will contain a calculation example. For open burning, it will discuss the basis of the NEI estimates and important variables affecting emissions. It will also offer suggestions for making improvements to the inventory. A detailed example of residential wood surveys is included, and wildfire inventory development will be covered in much more detail. Thank you for your interest in combustion source emissions.